In question 1, we've got two particles P and Q. They are moving in the same direction along the same straight line when they collide. Immediately before collision, we've got the speeds of P and Q. And immediately after they collide, they both move in the same direction with the speed of Q being 4 times the speed of P. I will start by drawing a diagram. We've got P and Q. The masses are m and 2m kilograms respectively. Let's assume they were both moving to the right. So we had P moving with 4 u meters per second to the right and Q with u meters per second to the right. And immediately after they collide, they are both moving in the same direction. Now we know that they should be moving to the right. So P is moving to the right with a speed of v meters per second, and Q is moving to the right with a speed of 4 v meters per second. We need to find the speed of Q immediately after the collision, so I will be using conservation of momentum. So the momentum before the collision was m times 4u plus 2m times u, and this is equal to mv plus 2m times 4v. So we have that 4mu plus 2mu is mv plus 8mv, leading to 6mu being 9mv. Now the m cancels out, and we get that the v is 6u over 9. We are after the speed of Q immediately after the collision, so we want to find 4v, and therefore we get that 4v is 4 times 6u over 9, which simplifies to 8u over 3 meters per second. In part B, we need to find the magnitude of the impulse exerted by Q on P in this collision. And we do know that the impulse exerted by Q on P is simply the change in momentum of P. So the change in momentum of P will be the momentum after, so mv, minus the momentum before collision, m times 4u. We have already found v to be 2/3 of u, so m times 2/3 of u minus 4mu. So this is 2mu over 3 minus 4mu, which leads to minus 10 over 3mu. And therefore the magnitude of the impulse will be simply 10 over 3 mu Newton seconds. In part C, we need to state clearly the direction of the impulse. Well, based on the calculation we did here, we found a negative answer, which means that this is opposite the direction of motion of P. The negative sign indicates this opposing direction, and therefore for part C, we simply state that it's opposite the direction of motion of P. In question 2, we've got a small ball thrown vertically upwards with a speed of 14.7 meters per second from a point 19.6 meters above horizontal ground. We need to determine the total time from when the ball is thrown to when it first hits the ground. It makes sense to draw a diagram here. So this is what's happening here. We've got the ball initially here. It leaves with a velocity of 14.7 meters per second pointing upwards. It's at a height of 19.6 meters here. And we know that acceleration is opposing motion, so acceleration is minus 9.8 meters per second squared. I need to find the total time until it first hits the ground. So when it hits the ground here, we know that the displacement will be minus 19.6. So I'll be using S is ut plus a half at squared. So S is minus 19.6 is equal to 14.7 t plus a half times minus 9.8 t squared. This leads to minus 19.6 is 14.7 t minus 4.9 t squared, and therefore we get that 4.9 t squared minus 14.7 t minus 19.6 is equal to 0. I will be using the quadratic formula here. T is minus 14.7 plus minus minus 14.7 squared minus 4 times 4.9 times minus 19.6 square root over 2 times 4.9. We get two solutions. We get that t is 4 or t is -1. Obviously, the negative solution is rejected. It's not valid. Time is always positive, so we reject that t is -1, and we conclude that the time taken was 4 seconds. In part B, I need to find the speed of the ball immediately before it first hits the ground. So in this case, I will be using v is u plus at. We know that the initial speed u was 14.7. The acceleration is minus 9.8. The time was found to be 4. So this gives velocity to be minus 24.5 meters per second. The negative sign is indicating that it's coming down. We were asked to find the speed. Speed is always reported in a positive sense. So speed is 24.5 meters per second. In C, we need to determine the total distance traveled by the ball from when it is thrown to when it first hits the ground. So I will redraw my diagram here. We know that we reach a maximum height. So at this point here, it's the maximum height reached. At this point, the velocity is 0 meters per second. So the ball is instantaneously at rest. And we would like to find the height h. Because once we find this height h, it means we go up by h, we come down by h, and then we add another 19.6, and this will give me the total distance traveled by the ball. I will be using v squared is u squared plus 2as. We know that 0 squared is 14.7 squared plus 2 times minus 9.8 times h. So 0 is 216.09 minus 19.6h, and therefore 19.6h is 216.09, which leads to h being 11.025, and therefore we conclude that the total distance traveled until it first hits the ground will be 2 times the 11.025 plus the 19.6. This gives an answer of 41.65. If I stick to this answer, I will be penalized since I'm using g to be 9.8. I round this to 3 significant figures, so this is 41.7 meters. In part D, we need to sketch a velocity time graph for the motion of the ball until it first hits the ground, and we need to state the coordinates of the starting point and the end point of the graph. So we know that throughout this motion, acceleration was constant at minus 9.8. We know that the acceleration is the gradient in a velocity time graph. So we're looking at a straight line going downhill as shown here. We know that we cut the velocity axis at 14.7. That's the initial velocity. We know that the time of flight was 4 seconds. And when t was 4, velocity was found to be minus 24.5. So this is the completed velocity time graph for the motion of the ball. In question 3, we've got the particle here. It has a mass of 10 kilograms. It's on a rough inclined plane. Tan alpha is 3/4, and it's held in equilibrium by a force of magnitude p newtons. We have been told that the coefficient of friction between the particle and the plane is 1/2. We need to find the normal reaction between the particle and the plane. I will start by drawing a diagram here. This is what we have. The weight is 10g. I will resolve the weight perpendicularly to the plane. So there it is. We know that the angle here is alpha, and therefore this is 10g cos alpha. And therefore the reaction here, which I will call R, is simply 10g cos alpha. Now to find cos alpha, I will draw a triangle here. We have that tan alpha is 3/4. It's a 3, 4, 5 triangle, and therefore we can easily see that sine of alpha is opposite over hypotenuse and cos of alpha is adjacent over hypotenuse. So r is 10g cos alpha, which is 10g times 4 over 5, and this turns out to be 78.4 newtons. In B, we need to find the greatest possible value of P, and to do that, I need to consider the forces acting along the plane. So we certainly have the force P here, and we have also the component of the weight acting down the plane. So this is gonna be acting down the plane. It's gonna be 10g sine alpha. We know that the greatest possible value of P will be at the moment where the particle is about to go up, and therefore the friction will oppose this. So we've got a frictional force here acting down the plane. Now we know that the frictional force F is equal to mu r. So it's going to be a half the value of mu times 78.4, which is the reaction, which is 39.2 newtons. And therefore, if I equate the forces acting along the plane, so forces acting upwards along the plane, P is equal to forces acting downwards along the plane is equal to 10g sine alpha plus F. So P is 10g sine alpha is 3 over 5. F is 39.2. This gives an answer of 98 newtons. In C, I need to find the least possible value of P, and the least possible value of P will be at the point where P is just enough to keep the particle here from rolling down. So since it's about to go down, the friction is no longer acting down the plane, it's acting up the plane, so it appears here, and therefore we will be having that P plus F is equal to 10g sine alpha. So P plus F, which was found to be 39.2, is equal to 10g times 3 over 5. So P is 10g times 3 over 5 minus 39.2, and this gives an answer of 19.6 newtons. In question 4, we've got a non-uniform beam AB with a length of 8 meters having a mass of capital M kilograms. The center of mass, we are told, is d meters from A, and now it's supported in equilibrium in a horizontal position by 2 vertical ropes at C and D. We've got a gymnast of mass 64 kilograms who stands at point X such that AX is 1.875, so the gymnast is somewhere here. And the beam remains in equilibrium in a horizontal position, but is now on the point of tilting about C. Now, if it's about to tilt about C, this means that there is no tension on D, so I will actually start by considering the situation as it stands now. I will start by adding the forces. We've got the gymnast with a mass of 64 kilograms, so 64g here at point X. We've got the center of mass at d meters from A, and the mass is capital M. So in terms of distances, the distance from A to the center of the mass is d meters, and the distance AX is 1.875 meters. Additionally, we've got the tension at C. I will call this TC. And we know that this distance here is d minus 2.5. So let me write this down. So this is d minus 2.5 meters. And additionally, this part here, this distance here is 2.5 minus 1.875. So 2.5 minus 1.875, which is equal to 0.625 meters. And I can now proceed by taking moments about C. we've got the capital mg here acting in a clockwise direction about c at d minus 2.5 meters, and therefore its distance times force the clockwise moment, so d minus 2.5 times capital mg, and this is equal to the anti-clockwise moment due to 64g, which is at a distance of 0.625 meters. So this is 0.625 times 64g. Now the g on either side cancels out. 0.625 times 64 is 40. So we've got d minus 2.5 times capital M is 40, which leads to M is 40 over d minus 2.5. We are then told that the gymnast dismounts from the beam, and we've got a second one of mass 48 kilograms now standing at point Y, where YB is 0.5 meters, and we now have the beam remaining in equilibrium in a horizontal position, but is now on the point of tilting about D. So if it's about to tilt about D, there is no tension at C. So once more, I will add the forces on my diagram. We've got the tension at D here, so this is TD. We still have the center of mass, so the mass is capital M, and this is at a distance of D meters from point A. We have the second gymnast with a mass of 48 kilograms, so 48g acting here. This is at a distance of 0.5 meters from B. This means that the distance between D and the gymnast is 1.5 meters. 2 minus 0.5. So this is 1.5 meters. And we also have that the distance of the center of the mass to point D here can be found by doing the total length of the beam, which is 8, minus the D, which is this part here, minus the 2, which is this part here. So it's 8 minus 2 plus D, and this is 6 minus D meters. We'll now take moments about D to determine another equation that connects D with M. We have a clockwise moment because of the 48g here acting in a clockwise fashion about D at a distance of 1.5 meters. So this is going to be 1.5 times 48g, and this is equal to the anti-clockwise moment due to capital mg, which is acting at a distance of 6 minus dm. So this is 6 minus d times mg. Once more, the g's will cancel out. 1.5 times 48 is 72, and this is equal to 6 minus d times capital M. So we've got that 72 over 6 minus d is equal to capital M, and I will now equate the two expressions we obtained for capital M. So we have that 72 over 6 minus d is equal to 40 over d minus 2.5, and we proceed to cross multiply. We've got 72 times d minus 2.5 is 40 times 6 minus d. This expands to give 72d minus 180 is equal to 240 minus 40d, and therefore we've got 112d is equal to 420, which makes d 3.75. Remember, we are after the value of capital M, so I will go back and substitute into the expression here. So capital M is 72 over 6 minus 3.75, and this turns out to be 32. In question 5, we've got a particle P moving with constant acceleration. We've got the velocity here in terms of time in vector form. We need to find the speed of P when t is 2, so I will start by substituting t is 2 into the expression for the velocity. So v will be 7 minus 5 times 2i, and 12 times 2 minus 20j. This gives me a vector of negative 3, 4. We have been asked to find the speed, so I need to take the magnitude of the velocity vector. So the speed is simply minus 3 squared plus 4 squared square root. Remember, it's Pythagoras theorem, which gives an answer of 5 meters per second. In B, we need to find to the nearest degree the size of the angle between the direction of motion of P and the vector j when t is 2. We've got the velocity here when t is 2. Remember that direction stems out of the velocity vector. So I will start by drawing a vector corresponding to minus 3, 4. So the idea is to sketch a diagram to get a sense of what's happening. So this is what we have here. This is the vector minus 3, 4. We go 3 to the left and then we go 4 up. So we've got 3 here, we've got 4. The vector j is the unit vector that takes me up. So this is j here. We are trying to find the angle to the nearest degree between the two vectors. So we're trying to find the angle theta here, which is alternate angles with this one here. So this leads to tan theta being 3 over 4, and therefore we get that theta is shift tan of 3 over 4, which to the nearest degree is 37 degrees. Be careful here. If you decide to go for more accuracy, you will be penalized because you've been asked to give your answer to the nearest degree. In C, we need to find the acceleration A in terms of I and j. We know that acceleration is the derivative of velocity, so the acceleration vector is dv dt. So if I differentiate the velocity, I get minus 5i plus 12j. Remember, the constants vanish and it's just the coefficients of t essentially, and this is in meters per square second. And finally, in D, we need to find the value of t when p is moving in the direction of the vector minus 5i plus 8j. So if p is moving in this direction, it means that the velocity at this time is parallel to this vector. So essentially, we've got the vector minus 5, 8, which is parallel to the velocity vector, which in general form is 7 minus 5t, 12t minus 20. So these two vectors are parallel. It means that the ratio of the I components and the j components is the same. So this leads to minus 5 over 8 is equal to 7 minus 5t over 12t minus 20. I will proceed through cross multiplication. So minus 5 times 12t minus 20 is 8 times 7 minus 5t. So minus 60t plus 100 is equal to 56 minus 40t. So we've got that 44 is equal to 20t, and therefore it's 2.2 seconds, the value of t, the time at which the particle is moving in the direction of minus 5, 8. In 6, we've got a railway engine of mass 1500 kilograms attached to a railway track of mass 500 kilograms by a straight rigid coupling. The engine is pushing the track up, so this is the engine and this is the track, and this track is inclined at an angle satisfying that sine of alpha is 7 over 25. Now the engine produces a constant driving force of magnitude d newtons, and the engine and the track experience resistance to motion of 1200 and 500 newtons respectively. Additionally, we are told that the thrust is 2000 newtons, and we need to find the acceleration of the engine and the track. I will start by considering the diagram here, and I will start adding all the forces acting on the track and the engine. So I will start with the weights. The engine here has a weight of 1500 g, so the component which is perpendicular here is 1500 g cos alpha, and similarly for the track it's gonna be 500 g cos alpha. We've got the acceleration acting in the upward direction. So I will call this A meters per square second. And additionally, we've got the component of the weight acting down the slope, down the track. So this will be 15g sine alpha. And for the track, it's gonna be 500g sine alpha. Additionally, I need to include the resistive forces, so it's 1200 newtons for the engine and 500 newtons for the track. And then I need to add the coupling, so we need to consider that the track here is feeling being pushed up the track. So the force is acting in this direction here and has a magnitude of 2000 newtons. And similarly, the engine is feeling the same and opposite force. So 2000 newtons here. And we also have got the force provided by the engine of magnitude D newtons. So this is here. So this is capital D. And we need to determine the acceleration of the engine and the track. So I will start by considering the track. So I will encircle all the forces acting on the track here. So considering the track, we've got forces acting along the direction of the acceleration, which is 2000, minus forces opposing this, which is 500g sine of alpha plus 500, and this is equal to mass times acceleration. The mass is 500 kilograms, the acceleration is a. So we have 2000 minus 500 times 9.8 times sine of alpha, which is 7/25, plus 500 close brackets is equal to 500 a. And this leads to 128 being 500 a, and therefore the acceleration is 0.256 meters per square second. In part B, we need to find the value of D, and to do that I will consider the forces that are now acting on the engine. So considering the engine, we've got the force acting up the track, which is D, minus the forces that are acting in the opposite direction, so 2000, which is the force in the coupling, plus 1500g sine alpha plus 1200, and this is equal to mass of 1500 times the acceleration, which is found to be 0.256. So this leads to D minus 2000 plus 1500 times 9.8 times 7/25 plus 1200 close brackets is equal to 384, and therefore D minus 7316 is equal to 384, which leads to D having a value of 7700 newtons. In question 7, we've got two particles A and B with masses 5m and 3m respectively. They are connected together with a light inextensible string. Then string passes over a small, smooth, light, fixed pulley, and we release particle A, and we need to find in terms of m and g the magnitude of the force exerted on the pulley by the string while A is falling and before B hits the pulley. I will actually go to the diagram here and start by adding all the forces. So we've got the weights of B and A, 3mg and 5mg respectively, and we've got tension in the string. Tension is pointing upwards, and it's the same tension throughout the string. We'll call this capital T. Now A is heavier than B, so A will go down and B will go up. They experience the same acceleration as the string is inextensible, and then we can form equations for motion for A and B respectively and combine them to get the tension in the string. So considering A, we've got forces acting downwards minus forces acting upwards is mass times acceleration. So we've got that 5mg minus capital T is 5ma. Similarly, considering B is moving upwards, so forces acting upwards minus forces acting downwards is mass times acceleration. And therefore, this means that I can combine these two simultaneous equations. I can multiply the first one by 3. This will give me 15 mg minus 3t is 15 ma. And then I will multiply the second one by 5. This leads to 5 capital T minus 15 mg is equal to 15 ma. And therefore, since both of them are equal to 15 ma, I can say that 15 mg minus 3t is 5 capital T minus 15 mg. So 30 mg is 8 capital T, which leads to 15 mg over 4 is equal to capital T. So we just found the tension that's acting here in this system. We now need to consider the pulley to see the forces acting on the pulley in order to determine the magnitude of the force exerted on the pulley by the string. So this is the pulley here, and if you think about it, the pulley is feeling a tension on either side of it due to the string going over it, and therefore we can say that the force that's exerted on the pulley is simply the sum of these tensions. So the force exerted on the pulley is simply 2t, and we just found t to be 15 mg over 4. So this is 2 times 15 mg over 4, which is equal to 15 mg over 2 newtons. In B, we are asked to state how we have used the fact that the pulley is smooth. Well, obviously, if the pulley is smooth, there is no friction as the string passes over it, and therefore the tension is the same across the pulley. So this is simply what we need to state here. There is no friction, and hence the tension is the same across the pulley. We need to mention the pulley here, otherwise we will be penalized. In question 8, we are being given the acceleration time graph for a journey made by a car along a straight horizontal road, and we need to find the distance traveled by the car during the first 4 seconds of its journey. Now notice that over the first 4 seconds of the journey, we've got a constant acceleration of 3 meters per square second, and therefore we can use the Suvat formulae. So we know that we start with an initial velocity of 0 meters per second, as we were told that the car accelerated from rest. The time taken was 4 seconds, and the acceleration was 3 meters per square second, and therefore we can simply use S is ut plus a half at squared. So S is the distance, 0 times 4 plus a half times 3 times 4 squared, and this gives an answer of 24 meters. In B, we need to find the total distance traveled by the car during the first 26 seconds of its journey. So we already found the distance covered in the first 4 seconds, and we need to find the distance covered during these 20 seconds and then during these 2 seconds in order to add them up and find the total distance covered. So actually for part B, I will start by finding the speed when t is 4, because this will be the initial velocity for the second leg of the journey between the 4th and 24th second. So when t is 4, I will be using v is u plus at. So the speed when t is 4 is simply the final speed for the first leg of the journey. We started off at rest, so u was 0 plus 3 times 4. So this is 12 meters per second. And then we need to find the distance between t is 4 and t is 24. We have the initial speed, we have the time, we've got the acceleration. So we're pretty much following the same approach we did in part A. So here u is 12 meters per second, t is 20 seconds, and a is 1.5 meters per square second. So I'm again using S is ut plus a half at squared. So 12 times 20 plus a half times 1.5 times 20 squared. And this gives an answer of 540 meters. So this is the distance covered between t is 4 and t is 24. And I will now repeat the process. So find the speed when t is 24 to find the distance covered during the last 2 seconds of the journey. So the speed when t is 24, I will be using again v is u plus at. The initial velocity of the second leg of the journey was 12, as we just found here above. We had an acceleration of 1.5 for 20 seconds. So this gives 42 meters per second as the speed when t is 24. This is the initial velocity for the final third leg of the journey that lasts for 2 seconds. So the distance between t is 24 and t is 26 can be found by considering that the initial velocity was 42 meters per second, the time was simply 2 seconds, and the acceleration was negative 4 meters per square second. Again, s is ut plus a half a t squared. This gives an answer of 76 meters, and therefore the total distance covered over these 26 seconds will simply be the sum of the 3 distances. It's the 24 meters we found in part A, and the 540 and the 76, and this gives an answer of 640 meters. Now, an alternative approach for part B would be to try and draw the speed time graph from the acceleration time graph. We know that in a speed time graph, the acceleration is simply the gradient. So I could start by drawing a pair of axes here. It's the speed and the time. We know that for the first 4 seconds, we've got a gradient of 3, so something like that. Then a gradient of 1.5, and a gradient of negative 4. I will start adding the information here. So the first leg of the journey is at 4 seconds. The second leg of the journey finishes at 24 seconds, so somewhere here. And finally, the end of the journey is at t is 26. So we also know that the gradients are 3. The gradient here is 1.5, and the gradient is negative 4. So using the fact that the gradient is a rise over run, then we can easily see that the height here should be 12, so that 12 over 4 gives me the 3. And then we know that the run here is 20, so I will draw a dotted red line here. This is 20. And so we can find that the rise here is 20 times 1.5, which is 30. So the speed has increased from 12 by another 30. So it is now at 42. So let me write the 42 here. And over the last leg of the journey that was lasting for 2 seconds, the gradient was negative 4. So this means we've dropped by 8 here. So from 42, we are now down to 34. So I've got all the necessary information here. So I'm now going to be using the fact that the area under a speed time graph is simply the distance. So I have just shaded the 3 areas I need to find, and for each of these I'll be finding its area, which will be the distance covered. So for the first one, it's simply a triangle, so it's gonna be base 4 times the height of 12 over 2, which is 24 meters, which agrees with the answer in part A. For this second region, it's a trapezium. It's base 1 plus base 2 over 2 times the height. So in this case, we have 12 plus 42 over 2 times the height of 20, which gives 540 meters. And finally, we've got another trapezium at the very end. Base 1 is 42, base 2 is 34. the height is simply 2. So this will be 42 plus 34 over 2 times 2, which gives an answer of 76 meters. And therefore the total distance covered will be the sum of these three figures, 24 plus 540 plus 76, which gives an answer of 640 meters, which agrees with the answer we found with the alternative approach.